In case you hadn't had enough review of electron movement arrows and carbocation stability, you're about to get a lot more in Chapter 23. So, Chapter 23 really just covers electrophilic aromatic substitution in greater depth. And what we'll be focusing on in this particular mini lecture is kind of the introductory stuff in sections 1 through 4, which really pound regiochemistry into your head. So, it's electrophilic aromatic substitution over and over again. The upshot, the 3 R's, and I don't mean reading, writing, and arithmetic. Regiochemistry, reactivity, and most importantly, review. So we did a little review, this review in particular in class, where we said, okay, if I add an excess of HBr to an alkyne, do I get the 1,2 dibromo species or the 2,2, or in this case 3,3 dibromo species? And you will recall, yeah, the 2 bromines end up on the same carbon because of carbocation stability. That when that second addition of HBr takes place, we have to think about regiochemistry at this point. Are the pi electrons going to come out and get protonated to give you that carbocation, the charge on the carbon bearing the bromine, or the charge on the carbon not bearing the bromine? And the answer is the most stable carbocation is going to be formed, which is this guy, because of that resonance contributor. So even though bromine is electron withdrawing, that donation of the bromine lone pair to delocalize that positive charge is a big plus. So we're going to see the exact same thing in electrophilic aromatic substitution. When we look at adding an electrophile to an aromatic ring that already has a substituent on it, as in anisole here, we want to nitrate it. Obviously, if we think about symmetry, we realize there's 1, 2, 3 different kinds of hydrogens on here, so we should expect 3 possible products. But none of the meta, or very little of the meta, is formed. An insignificant amount. Why would that be? You pretty much already know the answer. It's because of carbocation stability. So, looking at the reaction mechanism, okay, if I take that pair of pi electrons and react it with my nitronium ion electrophile, which I don't really have room for here, then, woohoo, there we go. One possible intermediate is the one shown in the lower left. And when you look at that intermediate, of course you can delocalize that pair of pi electrons, and you can delocalize that pair of pi electrons, but the main thing that you can do when you have the positive charge on that particular carbon is you can use the lone pair on oxygen to delocalize it. So that's an extra resonance contributor that's only possible when we've put the substituent on the ortho position. Or is it? When we put the substituent in the meta position, so for example, now I'm looking at this pair of pi electrons reaching out and grabbing NO2+. Well, I get this intermediate. Okay, there's my positive charge. Look at this resonance contributor, and what have I done? I've again managed to put the positive charge on the same carbon that bears the oxygen. So again, I have that extra stable resonance contributor. And I know what you're thinking. Oxygen doesn't want to have a positive charge. Well, that's not true at all. We see oxygen with a positive charge all the time. There's a really very common example right there. What we don't like to see is an oxygen with 6 electrons and a positive charge. But this guy still has 8 electrons, so it's not that bad. So, take-home message here is that for ortho and para substituents, we can still get that extra added stable resonance contributor. Meta, not so much. When I try to delocalize my pi electrons, I can get the positive charge on that carbon, I can get the positive charge on that carbon, and obviously I can get the positive charge on that carbon. But I can never, ever, ever get the positive charge on that carbon. Therefore, that's a less stable intermediate. It has one fewer resonance contributors that makes it the less likely to form, less stable. So, simply put, for directing effects in electrophilic aromatic substitution, there's basically just two kinds of directors: ortho-para directors and meta directors. So, as we've just seen, ortho-para directors are ones like anisole that can push lone pairs or somehow or other release electron density into the ring to stabilize that carbocation intermediate. Well, look at the example on the bottom, toluene. We know alkyl groups are electron releasing. No, they don't have a lone pair, but that was our whole rationale all through the course as to why a tertiary carbocation is more stable than a secondary carbocation and more stable than a primary carbocation, because each of these alkyl groups is electron releasing due to the electron density around the alkyl group and in the molecular orbitals. So if you have an electron donating substituent, you have an ortho-para director. Meta directors, just the opposite. When we have electron withdrawing substituents like the cyano group or the nitro group, where, if I have a cyano group, what do I have? I have the inductive effect of the nitrogen pulling electron density away from the carbon, but I also have resonance that puts a full positive charge on that carbon. So that is very, very definitely an electron withdrawing group. That's supposed to be an arrow. Doesn't really look like one. And for the nitro group, we've already seen the Lewis structure for the nitro group multiple times. That's about the best electron withdrawing group there is. So, electron withdrawing groups tend to be meta directors. A really easy, quote-unquote, way to see this is if I were to draw the resonance contributors for nitrobenzene, you will see that I end up being electron poor at the ortho and para positions. Well, now, if those are electron poor, there's no way in God's green earth that an electrophile is going to react at the electron poor centers. So the bottom line for understanding regiochemistry for electrophilic aromatic substitution is just thinking about polarity and thinking about kind of the kinetics of the reaction, the energy diagram. If I have two possibilities, the more stable rhenium ion is going to be formed a lot more quickly, and that's going to lead to the major product, because electrophilic aromatic substitution is under kinetic control, being that the first step is a doozy. No, the first step is the slow step, the rate determining step. Okay, so how do you keep it all straight? Piece of cake. You do not memorize. You think about, you draw and think about the resonance contributors for the carbocation intermediate for each particular example. Oh, yeah, no, that's the key to success in all of OChem, not just Chapter 23. So let's go through some examples. First one, let's look at this. It looks like a substituted aniline. It's some kind of amide. Okay, so what we have here is an electron donating substituent, because it has a lone pair on the atom attached to the ring. So in a fashion similar to the nitro example I just gave you, we can also look at the resonance contributors prior to addition of the electrophile and see that if I just go around the ring, I will see that in this particular example, we've got electron-rich carbons at the ortho and para positions. So, what I should expect to see is that when I add my bromine electrophile, okay, so I will have just, let me erase some of these arrows before this gets totally messy. When I go out here and grab my Br+, I put my positive charge right there, and delocalization. Takes me to that carbocation. And then, aha, there we go. Oops. We've got the magic resonance contributor that allows me to show that fantastic delocalization onto that heteroatom, the nitrogen. So that makes it more stable, and we can go through the whole sequence with para as well. The key being, once again, getting that positive charge, make sure that shows up, getting the positive charge on that carbon bearing the nitrogen. Alright, how about chlorobenzene? Well, first off, we know that these two react together to give us, again, that nitronium ion intermediate. And if I go ahead and pick a pair of pi electrons, any pair of pi electrons, given that this is an electron donating group, I would expect to see a mixture here of the ortho-substituted and the para-substituted nitro group. But let's look at the resonance contributors. So, showing that first electron movement, we've got the chlorine. We end up Putting our NO2 group there. Leaves me with a positive charge right there. Can I get the positive charge delocalized onto the carbon bearing the chlorine? And absolutely I can. There it is. And there's our final resonance contributor for illustrating the para-directing chloro group. All right, what about this thioether? Now remember these conditions here. What we're talking about is Friedel-Crafts alkylation, that we are generating. It's hard to make a dotted line with this puppy. Delta minus, delta plus. We're basically starting to break that bond. Maybe I'll just use a gray there. Consider that a partially formed bond. Okay, so we've got our ethyl group here, more or less. Jeez. Looks like I just woke up. Okay, so there is our electrophile. Let's try making this go meta. So there we go. Kick that out. So if I think this is going to be meta, then I put my ethyl group in the meta position. That leaves me with the carbocation right there next door. And I start looking at my resonance contributors. Positive charge. And I'm going to just put ETH. Okay. Swing those pi electrons all over creation. And what we see is phooey. I never get a chance to push that lone pair into a positive charge and take advantage of the delocalizing ability of my thioether. So this is not going to be a meta substituted outcome. No, once again, because we have an electron donating group on the thioether, because of the lone pair, it's definitely going to be ortho-para substitution. So you should be aware that in electrophilic aromatic substitution, when you get these kinds of outcomes, you do get a mixture. So you are not lucky enough to get only ortho or only para. Nope. When you get ortho, you get para. Sometimes sterics can get involved and you can get a major and a minor product, but you get a mixture and you're going to have to separate these out, usually by chromatography. And this would be a great question, like would you expect these to have the same or different polarities, same or different melting points, etc., etc., etc. Good old physical properties review. Okay, so that's it for the big intro overview. Practice drawing resonance contributors and you will be set. See you in class.